We'll list few of the relations which are possible on exclusive OR and on exclusive NOR operation. A exclusive OR with A, it is 0. A exclusive NOR with A, it is 1. A exclusive OR with 0, it is A. A exclusive NOR with 0, it is A complement. A exclusive OR with 1, it is A complement. A exclusive NOR with 1, it is A. A exclusive OR with A complement, it is 1. A exclusive NOR with A complement, it is 0. In fact, what is the list we are looking here? All these relations are known for us because while discussing the truth tables of exclusive OR and exclusive NOR, we already listed this type of information, maybe with a different meaning there. So if you go back to the video or if you go to the notes, the notes you made, while discussing XOR and XNOR, you are looking to this type of results with a different meaning as whenever one of the variable of XOR is 0 or whenever one of the variable of XNOR is 1 or whenever both are same, whenever both are not same, like this. With that meaning, we already mentioned these results. So the same thing, of course, I am putting here in order, nothing else. So all these are the known thing for us. And a part of this, you can see few more. A complement exclusive or the B complement is equal to. So you're supposed to read this must be A exclusive or B. To verify this, possible to use either maybe Boolean algebra work or maybe possible to use the truth table. Suppose if at all we use the Boolean algebra procedure, we are looking here A complement exclusive or B complement result. Just for our convenience, let me speak. Let X is A complement. Based on this, X complement is A and also Y is B complement, so that Y complement is B. Now let us replace this A complement as X and B complement as Y. While expanding this by using the exclusive OR operation, we are having this as X complement Y or with X Y complement. Whereas X complement is A and Y is B complement. X is A complement and Y complement is B. So it is the SOP expression of XOR on A and B variables. We are started with this A bar exclusive or the B bar and we are reaching to A exclusive or B. Hence, the relation what we mentioned is true. In fact, as I said already, no need to go to such a lengthy work also. With a simple imagination also, you can understand how it is so. When we are having a question, A complement exclusive or the B complement, then we are looking in the truth table, the two variable, the first and last row will be interchanging. The first and last row is interchanging. The first row result, last row result is same 0. So no change. And also we are looking the middle two rows will be interchanging. We know the result of middle two rows also same. So effectively on the whole, without talking anything with a visualization while remembering XR truth table, without anything, we can accept this A complement XR B complement result must be equal to A exclusive or B. The similar one You can read on exclusive NOR. A complement exclusive NOR B complement must be equal to A XNOR B. A exclusive or B complement, you can guess easily because we already covered this. It is equal to A XNOR B. While doing one of the problem, before coming to this listing, while doing one of the problem, we come across similar sort of expression as a part of the question. So we already verified there, this A exclusive or B bar is equal to A XNOR B. As similar to this, you try yourself, A XNOR B bar must result as A exclusive or B. You try yourself. If any difficulty, you can post as a question. So the Telegram channel, what is the channel are available, we can contact, we can discuss. But hopefully that is not the case. You can do on your own. As similar to this, what we did earlier, the same work we extend, you'll be having a conclusion A XNOR B bar is equal to A exclusive or B. Next, let us come. If A exclusive or B is equal to C, then A exclusive nor C is equal to B. B exclusive or C is equal to A. Finally, A exclusive or B exclusive or C is equal to. By this time, you supposed to guess the result of this must be equal to 0. Because A exclusive or B based on the statement, it is C. A exclusive or B based on the statement is C. So C exclusive or C, this is a known thing for us. We are having here also. And of course, for the truth table, we know C exclusive or C must be 0. So this is 0. And coming to this, among these two, we need to check for one. While checking for one, default other is valid. The verification of this possible either may be with the help of the truth table or maybe with the mathematical expansion work. Suppose if you work out with the help of the truth table, A exclusive or B result is mentioned as C. So 0, 0, 0, 1, 1, 0, 1, 1. We are looking here 0, 1, 1, 0. Later, if you take this expression, say A exclusive or C expression, let us take. For A exclusive or C, it is nothing but XOR between the first column and the third column. 0 XOR with 0 is 0. 0 XOR with 1 is 1. 1 XOR with 1 is 0. 1 XOR with 0 is 1. So we are looking here. This result is coming same as column B. Once this result is coming same as the column B, then what we mentioned is true. What we mentioned is true. So based on this, of course, you can accept this second one, or if at all we are having time to do, definitely you can try on your own. On your own, if you try, you'll be having this also as true result, as a true relation. Similarly, let us come to the next one. If A exclusive nor B is equal to C, then A exclusive nor C is equal to B. B x nor C is equal to A. A x nor B x nor C will be equal to, you can try, it must be equal to 1. It must be equal to 1 because A x nor B is possible to read as a C. C x nor C, based on the second result, it is 1. And the verification of this will be similar to the verification what we are having with XOR. So try yourself. Hopefully you will be get. It won't be any problem. You will be getting. If still any difficulty, you can post the question in the Telegram channel or what are the feedback channels we are having through. You can speak. Hopefully that is not the case. You can do on your own. In fact, it was the question once in the GATE CS paper. What I remember, it was a question in the 2000. It is given even in the workbook also. It was a question in the 2007. GATE CS paper, in fact. Based on this, we are having a question there. You can try on your own that question. The answer, of course, D. It is given in the try yourself. The answer also printed there. Let's come to the next one. If A exclusive or B exclusive or C is equal to D, then A exclusive or B exclusive or D is equal to C. A exclusive or C exclusive or D is equal to B. B exclusive or C exclusive or D is equal to A. And also, A exclusive or B is equal to C exclusive or D. B exclusive or C is equal to A exclusive or D. And A exclusive or C is equal to B exclusive or D. The last one, A exclusive or B exclusive or C exclusive or D is equal to, you can speak easily, it must be equal to 0. Because the statement of the property A exclusive or B exclusive or C is mentioned as a D. Once it is mentioned as a D, it must be D exclusive or D. Once a D exclusive or D using the first relation, we are speaking it is 0. From this list, try to verify once. From this list, try to verify one. Once we are verifying one from this, default, other two things will be valid respectively. The verification of this, similar to the verification of this 13. The 13th relation was on 3 variables. The 13th relation was on 3 variables. We were using 2 variable truth table to check the 13. The 15th we are looking the relation on 4 variables. Then definitely, as similar to this, we have to speak, we need to use a 3 variable truth table. 13 was on 3 variables, we were using the 2 variable truth table, and the 15 is on 3 variables, 15 is on 4 variables, so that we must use the 3 variable truth table. So with the help of the 3 variable truth table, if you try, all these results are coming to be true. So check yourself. If any difficulty, you can post a question. We'll be having, of course, without any problem. The work is coming to be true. You can verify easily. These relations are true. So these are the few important relations what are possible on this exclusive or on this exclusive NOR operation. It is one of the important lists, the relations what we mentioned, it is one of the important lists. Generally, you will be having questions based on this. In 2017 GATE paper, in 2018 GATE paper, there was a question related to this. So, practice well. They are not difficult things. They are not complex things. With a little practice, the questions what I said in the GATE paper, you can try. So, look to the previous solved GATE solution book. Look to the question, and instead of looking to solution, what is available in the book, try yourself. Hopefully, you can do all those questions. What I said in 2017, it was a question. 2018, there was a question. In fact, I'm talking CS paper itself. Let us try a question. The propagation delay of each NOT gate, which is used in the given circuit, is 100 picoseconds. What is the frequency of the output signal? What is the frequency of the output signal V0? It is a question. The propagation delay of each NOT gate which is used in the given circuit is 100 picoseconds. What is the frequency of the output signal V0? The given circuit is so this is the given circuit. In fact, it was a question in 98 gate EC paper. It was a question for 2 marks. So the circuit what we are having, which is basically built by using NOT gates. And this circuit is supposed to be named as a feedback circuit. If you are having little knowledge on the electronics, the wording what I mentioned, you might be catched. It is to be named as feedback circuit. In any electronic circuit, output is coming as the input. Such circuit we are naming as the feedback circuit. In this circuit, the output V0 coming as the input. So this is an example of the feedback circuit. And coming to the question description, each gate which is used in the circuit is having the propagation delay as 100 picoseconds. The word what we are looking here, propagation delay, in our discussion, the word we are using first time. So let us try to understand the means of the word propagation delay. For any hardware device, as and when we are feeding the inputs, the device won't respond instantaneously. To respond for the given inputs, the device will take certain amount of time to process the signals. So that after processing, we are having the response from the device. So how much time is involving to process? That time we are naming basically as the propagation delay. So after applying, in other way, alternatively you can speak, after applying the input to read the output, certain amount of time delay is involved. So that delay time we are naming as the propagation delay. Instantaneously we are not reading the readout. We need to wait certain time. The time we are naming as the propagation delay. In simple words, if you want to speak alternatively, you can note the propagation delay is the amount of time taken. The propagation delay is the amount of time taken by the logic gate. to respond for the given inputs. To respond for the given inputs. So it is a definition of the propagation delay. So based on this, if you say it is a NOT gate, after feeding the input, the NOT gate response we are having after 100 picoseconds. Now the question is, what is the frequency of the output waveform? What is the frequency of the V0 is the question. When we are taking the question, what is the frequency of the output waveform? Based on our basic knowledge on the signals, it is possible to speak. If the generated waveform is a periodic signal, if the generated waveform is a periodic signal, for such signal only we are having possibility to identify the frequency. For such signal only we are having possibility to identify the frequency. So that the waveform what's supposed to be generated by this circuit must be a periodic signal. For a periodic signal, with a fixed time interval, we are having a repetition of the waveform. So with what time interval we are having a repetition of the same wave shape, that time interval we are basically naming time period of the waveform. If the generated signal is not a periodic signal, if the generated signal is not a periodic signal, there is no question of talking the frequency on that. The generated signal is a periodic signal. While knowing the time period, one upon time period, we are calculating the frequency. The generated signal is not a periodic signal. There is no means of the wording using the frequency. So based on this, we are having understanding on this question as the question is definitely generating a periodic signal. It is generating a periodic signal. And if you look further, the components what we are having here in the circuit are the digital components. Once we are having digital components, the waveform what is generated is mostly a square wave signal, or maybe a rectangular signal, because we are having the logic devices, logic gates. The logic gates are with 1 or 0 values. Once it is 1 or 0 values, the waveform is supposed to be a square wave or may be a rectangular wave. Definitely, it is not coming to be a trigonometric waveform. So mostly the generated waveform may be a square wave. Suppose we are having here the options on this question as 500 megahertz, B 1 gigahertz, C 2 gigahertz, D none of the above. So just try what's supposed to be the frequency of the output waveform. With all this background what I mentioned, what's supposed to be the frequency of the output waveform? So if you try well, the answer is supposed to be this. If you try well, the answer is supposed to be 1 gigahertz. So let's look how it is so. Few of you might be speaking the answer may be this, it is wrong. The answer is 1 gigahertz. So let's look how it is so. Consider the output say as a 1. Of course, may not be 1. If you want, we can start even with a 0 also. So that 1 is coming as the input of first NOT gate. The first NOT gate output is 0 because it is inverter. Second NOT gate output is 1 because first NOT gate output is the input to this, and so on. If you look, third NOT gate output is 0, fourth NOT gate output is 1, and fifth NOT gate output is 0. So to switch from 1 to 0, how much time is involving? If you check, to switch from 1 to 0, this one is passing through these 5 NOT gates. Each NOT gate is having a propagation delay. Each NOT gate is having the propagation delay of 100 picoseconds. Hence, to switch from 1 to 0, 500 picosecond time is involving. 500 picoseconds time is involving. If you look as a waveform, this so what we are looking, initially we considered it is 1, it is coming to 0 after 500 picoseconds. If you want to calculate the time period, then this we should not read as a time period. If you want to calculate the time period, again we have to wait until the waveform is switching to 1, until the output is changing 0 to 1. Until to that we need to wait to identify the time period. So time period, if you want to speak, if at all we started with 1, we need to reach back to same 1. If at all we are starting with 0, we need to reach back to 0. Or if at all we are looking with waveform, it is giving more clarity for you. Initially it was 1, after 500 picoseconds it is reaching to 0. Based on this, it is not the time period. Until it is not coming to 1, we have to wait. So that based on this, don't calculate and don't come to a conclusion, the answer as a C. But all we are looking with this 500, 1 upon 500 picosecond, you may be reading wrongly, the answer may be as a 2 gigahertz. It is not correct. Now we are looking, the 0 is the input to the first gate, so first NOT gate output is 1, and so on. You can see here, it is coming back to 1. It is coming back to 1. So to switch again 0 to 1, the time involved is 500 picoseconds, because in this feedback loop, total 5 NOT gates, so 5 into 100 picoseconds, 500 picoseconds. So as a waveform, if at all we are looking now, so it is back to 1 after 1000 picoseconds. If you look like this, the same waveform is repeating like this. It is repeating like this. So from this we are recognizing the time period of the waveform is 500 plus 500. So that we are looking here, time period is 1000 picoseconds. Once the time period is 1000 picoseconds, then the frequency 1 upon time period, it is giving 1 gigahertz. So we are looking here 1 upon 1000 picoseconds. So if we evaluate well, the answer is coming as 1 gigahertz. So answer to this question is option B, if at all is a multiple choice. If it is a fill in the blank type, the answer must be 1 in gigahertz. It's supposed to be 1 in gigahertz. It was the question in the 98 gate paper, easy paper. It was a question for 2 marks. Now you have to look few of the points here. Instead of 5 gates, if at all in this feedback loop I am having only 4 gates, in this feedback loop, suppose I am having 4 gates. Then it is possible to speak the waveform what we are having here. This waveform is not a, can name same V0. The waveform what we are looking here, this waveform possible for us to speak, this is not coming to be periodic signal. It is not a periodic signal. If you check how it is so, the same way if you analyze, if you take here 1 is the input, so first NOT gate output is 0, second NOT gate output 1, third NOT gate output 0, fourth NOT gate output is 1. So if at all we are looking initially with a 1 output, the same 1 will continue. So no change in the output. Similarly, if at all in the beginning, if you say 0, the same 0 will continue. It means there is no repetition of the waveform. Once we are not having the repetition of the waveform, then definitely it is not a periodic signal. Once it is not a periodic signal, then generally speaking, ideal case if at all we are talking, generally speaking, we are not calculating frequency. So conclusion is, if we want to have the periodic signal generation with this sort of feedback circuit, then the number of gates which are to be present in the circuit must be, the number of gates which are to be present in the circuit must be odd number of gates. If you want to have the generation of the periodic signal, then the number of gates which are required must be odd number of gates in the feedback loop. Odd number of gates in the feedback loop or in the feedback circuit. Then only we are having possibility of a periodic signal generation. We are having odd number of gates, periodic signal is coming, but even number of gates we are having. Here we are having even number of gates. Ideally speaking, if at all, theoretically, the frequency will be 1 upon 0, infinite. The frequency will be 1 upon 0, no repetition. Sorry, very sorry. The repetition is at infinite time, 1 upon infinite. The frequency will be 0. For this case, the repetition time, theoretically speaking, infinite time, if you take 1 upon infinite, we are having the frequency as 0. So this is not generating a periodic signal. Whereas this is generating a periodic signal. When I am having odd number of gates in the feedback loop, so circuit as a matter of interest I am talking, it is mostly related with the electronics, electrical terminology. If you are having some knowledge earlier, it's okay. Otherwise, don't take anything much serious and don't bother to try anything much also. But as a matter of interest, I'm speaking here. It can be named as a stable multi-vibrator. It can be named as a stable multi-vibrator. A stable, normal English dictionary meaning you have to take, not stable. So what we are looking, the output what we are looking here, it is not stable. It is go on changing continuously, 1 to 0, 0 to 1 and so on. So based on this we are naming it is a stable multi-vibrator. So multi-vibrator is basically a circuit in the electronics terminology I am talking. It will generate a periodic signal. It is a square wave. So it is generating a square wave signal. This is generating a square wave signal, so that I must speak it is a stable multi-vibrator. Again I am repeating, you are having earlier knowledge of this terminology in your academic course, in your college. It's okay. If at all you are not having any such type of thing as a course in your syllabus, no need to bother. As CS students, not required to be, but definitely if it is electronics or electrical, I will insist to know well. Anyway, if you want to have the periodic signal generation in this feedback loop is consisting of from this point to this point, from where we are having connection, that only is to be named as a periodic signal. So in the feedback loop, if at all we are having odd number of gates, then we are having the generation of the periodic signal. Now, having odd number of gates, a general formula if you want to look per frequency calculation, assuming TPD is propagation delay TPD is a propagation delay of each NOT gate. TPD is a propagation delay of each NOT gate. Then formula will be 1 upon 2n TPD. 1 upon 2n TPD. For example, if you look here, n is 5. So 2n, it is 10. 10 TPD. TPD is, in this case, 100 picoseconds. So that 10 into 10, we said 1000 picoseconds based on this. So it is a formula what we can speak in such feedback circuit, assuming, be careful, assuming in the feedback loop we are having odd number of logic gates. Whenever in the feedback loop we are having odd number of logic gates, assume taking the TPD is a propagation delay of each NOT gate, the frequency of the generated waveform is 1 upon 2n into TPD. Suppose, as a matter of interest, if you look, we are having, after this fifth NOT gate, a gate is a buffer gate. It is buffer gate. So earlier question, if I say A bit, with this modification, let me speak, it is a B. So modification, what I am having is, I am having little extension to the previous circuit. The extension is, instead of reading the output after this fifth gate, earlier I was reading the output from here. Instead of reading the output from here, I am reading now the output after a buffer gate. Buffer gate output I am reading as the overall circuit. So buffer gate is producing the output always same as the input. Buffer gate will produce the output same as the input. If at all input is A, the same A is coming out. Such gate we are naming as buffer gate. So symbol is this. Without that bubble we are having, comparing the NOT gate, if you look, while looking to the symbol of the inverter and this buffer, if you see, the difference is, in the inverter or the NOT gate there is a bubble, but here there is no bubble. So basically such buffer gates are most of the times are used to provide some delays in the digital circuits. So come to this now. So here consider this buffer gate also having the propagation delay as 100 picoseconds. The buffer gate also having the delay as 100 picoseconds. And if I am talking the same question, what is the frequency of the output signal? If I am talking now, what is the frequency? What is the frequency of output signal Y? What is the frequency of the output signal Y? Earlier we were looking to the frequency of V0. Now our V0 is not the output signal. Based on this modification, as I said, B, the output signal we are talking as a Y. The question is, what is the frequency of the output signal? If it is a question, without any thinking, easily you need to speak, the answer to this question is remain same. The frequency is same, 1 gigahertz. So how it is so, you can understand as something like this. I am having here a buffer gate. This buffer gate is fed with a signal that is V0. The buffer gate is fed with a signal V0. So this buffer gate is getting the input V0. The output, if you look, buffer gate is not doing any modification in the wave shape. The buffer gate is producing output same as the input. So what you are having, the wave shape, overall wave shape is not changing. Only small difference is the output is available with a delay of 100 picoseconds. The output is available with a delay of 100 picoseconds. So waveform is shifting right by 100 picoseconds. So waveform is shifted by 100 picoseconds right. If you want little more clarity, I can put the waveform here like this. It is 100. It will be now 600. It will be now 1100. It will be now 1600 and so on. So the waveform had to look from here 100, and the pulse width should not change. Pulse width is 500 picoseconds. It is same. So pulse width is not changing means this one supposed to continue until to 600 picoseconds. Later it is 0. 0 for 500 picoseconds. 600 plus 500. So until to this 11 it must be 0 and so on. If we look, it is a waveform. So based on this, what we are looking, the time period we are interested to calculate, maybe from here to here or maybe from here to here. If you look, the time period is remain same. The time period is same 1000 picoseconds. As long as the time period is same 1000 picoseconds, the answer is same as the previous A bit. The answer is 1 gigahertz. So be clear when we are looking to this type of questions. To calculate the frequency, or basically after time period calculation, we are having a calculation for the frequency. To calculate the frequency, we need to bother the number of gates which are inside the loop. The number of gates which are inside the loop. That is important. Suppose in the B bit, what I am looking as a buffer gate. Instead of buffer gate, if I do here modification, this gate also a NOT gate, suppose. This gate also say NOT gate. So C, suppose. If this gate also NOT gate, if I am taking the question as say, what is the frequency of the output signal Y? What is the frequency of the output signal Y? Sorry, not Y, W. Let me take name. What is the frequency of the output signal W? Again, our answer to this question must be same 1 gigahertz. Answer to the question must be same 1 gigahertz. The difference is a small difference. What is the waveform we are having here? This waveform will be inverted. The waveform will be inverted because of the NOT gate. So once it is inverted, the time period is not changing. The time period is remain same 1000 picoseconds. Once the time period is remain same 1000 picoseconds, the frequency will be 1 gigahertz. So don't mix it. Here don't count as an even while using this NOT gate. While counting this, you don't say it is even. The number of NOT gates, what we are bothering is only in the feedback loop. The number of NOT gates, what we are having, what we are looking, they supposed to be in the feedback circuit or in the feedback loop. The NOT gate, what we are looking, which is outside the feedback circuit, that is not making any role for the signal generation. For signal generation, the role is coming only from this feedback circuit logic gates. The signal, what is the signal which is generated, that is from the point V0. So for generating V0, this is not having any role. Be clear. Don't mix, don't try some type of mug up of formula type of things. It is not good. If you are looking to formula type, be specific. As engineering way, you have to think. Number of gates, what you are talking, they must be in the feedback circuit. So as and when they are odd, then of course it is generating a periodic signal. The signal which is generated by this is to be inverted by this NOT gate, is to be inverted by the NOT gate with a delay of 100 picoseconds. With a delay of 100 picoseconds. This is to be inverted with a delay of 100 picoseconds. So to make it more little simple, as we consider the B bit with the buffer, so waveform what we are having, it is already delayed by 100 picosecond. If you comparing with the V0, this is delayed. This we are speaking as a Y. So Y is this means W is coming to be Y complement. So it is an inverted waveform what is said. Hence, we are looking here, the time period is remain same 1000 picoseconds. The answer to this question is 1 gigahertz. A similar type of question is available in the workbook. At two places, of course, it is available. One question is, with a similar knowledge, you can speak the answer on those questions. One question is in the try yourself, other question is not in the try yourself, other question is to work yourself. Question number 16. We're having the workbook, please open and check. Question number 16, this I am talking page number, and try yourself, of course, T7, page number 53. Question number 16, what we are having is exclusive OR gate we are having, and two NOT gates we are looking. A feedback loop is there. All the gates in the circuit shown below have finite propagation delay. The circuit can be used as a clock generator is the question. Clock is nothing but a square wave or rectangular wave, this type of waveform. So we are looking here in the question number 16. There are two NOT gates and one exclusive OR gate. In the feedback circuit, if at all we are looking odd number of gates in the feedback circuit, as and when odd number of gates are present, then that circuit can generate a square wave or a clock. It can generate. For generating clock, if you look to the based on the question, the exclusive OR must give the operation as a NOT operation. If XOR is operating as a NOT gate, then total number of NOT gates in the feedback circuit are 3. So odd, so square wave or a pulse signal or clock will be generated. So to use exclusive OR gate as a NOT gate, based on the question, X must be 1. Based on the question, X must be 1. So we already learned these things with XOR operation. X is 1 means the answer on this question will be option B. And similarly, if you come to the page number 53, we are having here a question. In this question, we are having NOR gates are connected in the feedback loop. 5 NOR gates are used. We are looking at a question, what is the frequency of the output waveform, assuming each NOR gate is having a propagation delay of 10 nanoseconds. So it is as similar as the question what we discussed as A bit. 5 gates, and the propagation delay here we took as 100 picoseconds. In this question is talking 10 nanoseconds in the try yourself, 10 nanoseconds. So based on this, if you work out well, you will be having answer in megahertz as the answer 10. The answer will be 10. So try yourself, you can do hopefully without any problem. Let us come to the next question. So it is a question in the workbook. The question number is 21. Question number 21. The workbook I am talking. Page number is 50. So you can open workbook and you can see the question what we are looking is, there is a circuit which is built by using a NOR gate and a exclusive OR gate. This gate is named as G1, this gate is named as G2, and also mentioned the propagation delay of the gate G1 is 10 nanoseconds, gate G2 is mentioned as 20 nanoseconds. And question what we are looking is, the input Vi is changing abruptly. It is changing abruptly 0 to 1 at t equal to 0. The input Vi is changing 0 to 1 abruptly at t equal to t0. Now, from the given options, we are having a question. What is the output waveform V0? What is the output waveform V0 is a question. So, you can speak now. Scaling, it is given, I think, in the question. T0 plus 10, it is a T0 plus 20. This is T0 plus 30. It is a T0 plus 40 and so on. In fact, you mentioned this as T1 is T0 plus 10. T2 is T0 plus 20 and so on, of course, in nanoseconds. So you can speak alternatively this as nothing but like this: T1, T2, T3, T4, T5 and so on. The question is, what is the output waveform V0? So, question what is available in the workbook, let me read as it is. The gates G1, G2 in the figure have the propagation delay as 10 nanoseconds and 20 nanoseconds respectively. If the input Vi makes an abrupt change from logic 0 to logic 1 at time t equal to t0, then the output waveform V0 is the question. Some ABCD options are given. From the options, we need to identify which is the waveform we are reading as the output. So we can identify which is the right waveform if and only if at all we are drawing the waveform to the V0, then only possible to pick the right answer. To draw the output waveform V0, it required for us to know both the inputs of this exclusive OR gate. One of the input of the exclusive OR gate is Vi, that is available in the problem description. But other input to the exclusive OR gate is from the gate G1 output. If you know the gate G1 output, then only we can speak now or we can draw the waveform for V0. After knowing the gate G1 output, it is possible for us to draw the waveform for V0. Hence, whenever we are trying to look the solution to this question, we need to try first the gate G1 output. We need to try for the gate G1 output. The gate G1 is NOR gate, but based on the connections we are looking here, its operation is a NOT operation. Its operation is inverted operation. And we are looking here, the gate G1, G2 are having the propagation delay of 10 nanoseconds and 20 nanoseconds respectively. While discussing the previous question, I already mentioned what is the definition of the propagation delay. So whenever we are feeding the inputs, the device is not responding instantaneously for the given input or inputs. The device is responding after certain amount of time. This amount of time we named as the propagation delay. So we are having some value addition with this propagation delay for each gate. While taking this value addition that the propagation delays into account, we need to draw the waveforms. So first we need to draw the waveform of the gate G1. Later we must try the gate G2 waveform. So if you look to solution, referring to this input signal, we need to start the solution. We are trying first the waveform of the gate G1. So output of the gate G1. So T0, T1, T2, T3, T4, T5, these definitions are already there in the problem statement. T1 is T0 plus 10 nanoseconds. T2 is T0 plus 20 nanoseconds and so on. So if you look here, before T0, the gate G1 input is 0. Once the gate G1 input is 0, the gate G1 output will be 1. The gate G1 output will be 1. So before T0, the gate G1 is with output of 1. Output of 1. At T equal to T0 plus, the gate G1 input is 1. Once the gate G1 input is 1, the gate G1 is an inverter, so that output must be 0. Because of this 1, output must be 0. But to give the output is 0, the gate need to wait. So the gate is waiting for 10 nanoseconds. Until 10 nanoseconds, it has to be the same previous value. After only 10 nanoseconds, it is getting the value as 0. It is as good as something like this. When you want to, while sleeping before night, you are kept alarm to wake up at say 6 a.m. Alarm may be ringing in your mobile at 6 a.m. but you may not wake up until say 10 minutes, 15 minutes. Until 10 minutes or 15 minutes, you will be still in the same phase. Same phase was sleeping phase. After 10 minutes or 15 minutes, you will be wake up, you will be alert. Same thing it is here. The gate G1 is getting the input at T0. It is getting alarm at T0, but it is not wake up at T0. It is wake up only after 10 nanoseconds. It means it is to be in the same phase. Phase was earlier it was 1. It has to be the same 1. After 10 nanoseconds, the gate G1 output is 0. Later, of course, the gate G1 input is 1, so the gate G1 output will be 0. So this is the output waveform of the gate G1. It is as good as speaking one of the input to the gate G2. It is one of the input to the gate G2. So we are looking here. These two waveforms together are inputs of gate G2. These together are the inputs to the gate G2. In fact, it was the input, one of the input, of course, only single input for NAR. Here we are having connection. So it is input of gate G1, you can speak. So these together are the inputs to the gate G2. Now if you look to the waveform, so gate G2 also lazy. Whenever we are feeding the inputs, it is not responding. Because of its laziness, it is responding only after 20 nanoseconds. Lazy, I'm talking as a delay. So, because of its delay, it is responding only after 20 nanoseconds. Okay. Here, from the known exclusive or truth table, we are trying to draw the waveform. Whenever both the inputs to the XOR gate are same, the output is 0. Whenever both the inputs of XOR gate are not same, output is 1. Whenever both the inputs are not same, output is 1. Whenever both the inputs are same, output is 0. It is a XOR truth table. Now, coming to this, your attention while working here is, whenever there is a transition for input signal, maybe any one of the input or maybe both. Whenever there is a transition for input signal, you need to keep attention. So at that time, there is a possibility the change in the output signal. So here we are looking before T0. If you look, one input is 0, other input is 1. At T equal to 0, we are looking input is changing to 1. So because of this, you need to have attention to draw the waveform. This is a waveform I'm talking V0 gate G2 output. It is output of gate G2. So to draw the waveform of this V0, our attention one point is at T equal to T0 because input is changing 0 to 1. And other attention we need to have at T equal to T1. So at T equal to T1, of course, we are looking one of the input is changing. One of the input is changing 1 to 0. So you need to be attention. At these 2 points, you need to give attention. So if you are framing this idea before drawing the waveform, then it is easy for us to speak further answer with more correctness. So if you look here, before T0, we are having one input is 0, other input is 1. Hence, before T0, the gate G2 output, that is overall circuit output V0, is 1. One input is 0, other input is 1, which is making XOR output is 1. Before T0, we are having V0 is 1. At T equal to T0 plus, both the inputs are 1. Whenever both the inputs are 1, XOR output must be 0. But XOR is, as I said, is a lazy. It is giving a response only after 20 nanoseconds. So that until 20 nanoseconds, it don't do anything. It is to be the same thing. It won't respond. It is with a sleepy mode. So it is with the same previous value. But after 20 nanosecond, it is getting alert. So after 20 nanosecond, it must change from 1 to 0. So at T equal to T0 plus, we are having both the inputs are 1. Because of this, the gate G2 must change. If it is a alert gate, if it is not a lazy gate, it must change. But it is a lazy gate, it is not changing at T equal to T0. To change, it is taking 20 nanoseconds. Until 20 nanosecond, it is to be the same earlier value. So that it is continue the same one until to T2. After T2, it is getting 0. It is changing from 1 to 0. Okay. Now, as I said, you have to trace the waveform changes. Other one trace, we are looking with the tracing. One point, we are looking at T equal to T0 change. Other point is at T equal to T1. So at T equal to T1, what we are looking? At T equal to T1 plus, one input is 1, other input is 0. When both are not same, XOR output must be 1. But to change this, to read this change from the XOR, it is to wait for 20 nanoseconds. So change is occurring at T equal to T1, T1 plus 20. So T1 plus 20 means at T3 we will be having a change. So that at T3 we will be having, it is 1. After T equal to T1, there is no change in the input signals. Once there is no change in the input signals, there is no any further change in the output. Hence, the output waveform of this logic circuit based on the associated propagation delays, it is a waveform. And from the given options, if you check, I hope the matching answer is option B. from the workbook, if you look, the answer, if you see, matching answer is option B. So quickly, I will repeat. Here the gate G1 is propagation, gate G1 is NOR gate, it is with a propagation delay of 10 nanosecond. NOR is effectively working as a NOT. Gate G2 is exclusive OR gate, it is having a propagation delay of 20 nanoseconds. Now overall circuit output V0 we want whenever the input VA is changing 0 to 1 at T equal to T0 is a question. So to draw the waveform of V0, we must try first the gate G1 output. It is a gate G1 output. So to draw the gate G1 output, if you look, we are looking before T0, the gate G1 is 0, so output is 1. At T equal to T0, input is changing 0 to 1. This change is giving effect on the gate G1 output. But to give the change, it is to wait for 10 nanosecond. So for 1, output must be 0, but it is only after 10 nanoseconds. It is only after 10 nanoseconds. After T0, there is no change in the input signal, so no change to the gate G1 input, so no change to the gate G1 output. These two waveforms together are the inputs to the gate G2. G2 is exclusive OR. XR output is 1 whenever both the inputs are not same. So knowing that, if you look here, before T0, one input is 0, other input is 1, so output is 1. At T equal to T0 plus, both the inputs are 1. Both the inputs are 1 means XR output is 0, but it is giving effect only after 20 nanoseconds. So T0 plus 20. After T2, it is giving 0. And if you trace like this inputs, if you look to the input signal, again change we are having a T equal to T1. One input is 1, other input is 0 at T1 plus. So because of this, we will be having output is 1. Of course, again after 20 nanoseconds. So T1 plus 20, T1 plus 20 means after T3, we are having output is 1. Hence, it is a waveform for the overall circuit V0. From the given options, we recognize the matching answer is option B. In fact, it was the question in 2002 GATE paper. For 2 marks, it was the question in the EC paper. A similar question was the question in 2003 GATE CS paper, a similar question. It was a question in the 2003 GATE CS paper. This question is given in the workbook. As a try yourself, I am mentioning the question number. Question number is 20, sorry. Question number is T19, page number 55. Page number 55. So the answer anyway, it is printed there. You try yourself. The due course after some time, after few video sessions, we'll discuss this question also. But in the meantime, you try yourself. The printed answer is available. Again, it was a question for 2 marks in the GATE 2003 question paper. There is a speciality for this NAND and NOR operators. This NAND and NOR operators are called functionally complete set operators. Functionally complete set operators. These are called functionally complete set operators. The corresponding logic gates we are naming as universal logic gates. The corresponding logic gates are named as universal logic gates. What are the means of this functionally complete or universal logic gates? If you see, for realizing any digital circuit, basically we are in need of few of these logic gates. By using few of these basic logic gates, it is possible for us to design any digital system. The digital system or the digital circuit may be a simple circuit or maybe a complex microcontroller or microprocessor. So any sort of digital system is possible to implement by using these logic gates. The group of these logic gates, with the usage of these logic gates, we are having implementation for any sort of the digital system. So coming to this, we are naming as the NAND and NOR gates are functionally complete operation. NAND and NOR operations we are naming as functionally complete set, and the corresponding logic gates we are naming as functionally complete set logic gates are universal logic gates. So meaning of the universal logic gates is, by using only NAND gates, if possible for us to implement the total digital system, or by using only NOR gates, if possible to implement total digital circuit, then of course, if it is possible, we are able to speak, we are able to prove it is possible, then definitely we are supposed to accept the NAND gate as a universal logic gate or NOR gate as a universal logic gate. So to prove the NAND is a universal logic gate or to prove the NOR is a universal logic gate, effectively the work what is required is, using only NAND gates or using only NOR gates, we supposed to implement all these basic logic gates. We supposed to implement all these basic operations. Once it is possible to implement, once it is possible to use only NAND gates to implement all these basic operations, basic logic gates, then definitely we are accepting based on this NAND is a universal logic gate or NOR is a universal logic gate. Let us try first with the NAND gate. By using NAND gate, it is possible not operation while giving the same input to both input lines. So while giving same input, its operation is A complement. From the truth tables, while listed some of the points there, while giving the truth tables of the NAND NOR, whenever A and B both are connected to same variable, the NAND is an inverter. So it is a NOT gate. So we are having here, it is a NOT operation. And if you try for this AND, the AND operation we are having basically by using two NAND gates. The second NAND we are having effectively the usage as the inverter. This is A, it is B, this is AB complement. So we are looking here, it is AB because we are looking AB complement is the input because of not one more complement. So effectively it is AB by using De Morgan's property. Or by say the fifth property what we listed in the properties list. And similarly, for OR operation if we try, the OR operation we are having by using three NAND gates. The first two NAND gates effectively we are using as inverters. It is A complement, it is B complement. So we are looking, this is A complement, B complement, whole complement. by using De Morgan's property, the result is, using De Morgan's property, the result is A or B. So this is our operation. Hence we are having possibility to implement all the basic logic gates just by using only NAND gates. Once that is the case, just by using only NAND gates, we can implement any sort of digital system or having possibility to realize any digital circuit. As similar to this, let us try with the NOR gates. So NOT operation, we are having the same input we are giving to both the inputs, so that it is a NOT operation. It is giving NOT operation. Or operation we are reading by using two NOR gates. The second NOR gate effectively is used as NOR gate. Second NOR gate is effectively used as a NOT gate. So we are looking here. The first NOR gate output is A or B complement. Hence, the second NOR gate output effectively A or B, because second NOR gate input is A or B complement. Because of NOT operation by the second NOR gate, finally the result is only A or B. It is OR operation. AND operation we are reading, we are implementing AND gate with usage of 3 NOR gates. By using 3 NOR gates, the first 2 NOR gates are used as inverters. So we are looking here, this is A complement or B complement, whole complement. So effectively this will be AB. It is AND operation. So we are having implementation of all the basic logic gates just by using only NOR gates. Hence NOR also functionally complete or universal logic gate. So based on this discussion, possible to speak, if we are having set of AND NOT, or we are having a set of OR NOT, the set of AND NOT or set of OR NOT itself functionally complete. The set of AND NOT is giving implementation for NAND operation. NAND we already proved as functionally complete. Similarly, the set of OR NOT is giving implementation for NOR operation. So NOR we already proved as a functionally complete or universal logic gate. Hence, if we are having a set of AND NOT or a set of OR NOT, the set itself functionally complete. You'll be having questions, maybe sometimes a simple question, something like this. Which one of the following set is functionally complete? A, B, C, D options will be having. One option A is AND OR, one option B is OR, XOR, something like this. So definitely one of the options supposed to be this, any one of this. Either it may be set of AND NOT or set of OR NOT is functionally complete. And from this you can see, so by using NAND gates, if at all we are interested to read NOR gate operation. To read the NOR gate operation, we are looking here, this OR operation as it is, and one more gate we are using as an inverter. If I speak, it is a W. W is Y complement. It is nothing but A or B complement. So it's a NOR operation. So for OR operation we are using 3 NAND gates. For NOR operation we need 4 gates. After OR operation we need one more gate as an inverter. And similar work we are looking here with an OR gate to implement NAND. To implement NAND, if you see here, we are having in need of one more gate. One more gate will be used as an inverter. So this, if you speak as a Y is Y complement, it will be AB complement. Hence, for implementing of AND, we are using 3 NOR gates. For implementing of NAND, we are using 4 NOR gates. For implementing of NAND, we are using 4 NOR gates. Let's try few problems. This problem is available, the workbook. The question is the minimum number of 2 input NAND gates required. The minimum number of 2 input NAND gates required to realize the function f. To realize the function f is a question. So it is a question in the workbook. I will tell you the page number and question number. Of course, the question in the second chapter. Page number 52, question number 41. Question number 41, page number 52, of course, chapter 2 I said. If you think and if you try little, hope you're supposed to get answer. If you try well, you're supposed to get the answer is to be 5. Whenever we are having a question of this nature, be clear yourself. Don't assume B bar is available. B bar won't available. Unless it is not mentioned, you need to consider when we are having this sort of questions, the variables are available only in uncomplimentary form. Unless it is not mentioned, you need to assume or you need to consider the variables are available only in uncomplimentary form. If it is mentioned, it's okay. But if it is not, nothing is mentioned, we must consider the variables are available only in uncomplimentary form. So B bar won't available. To get the B bar, normal situation, we need a NOT gate. Of course, here for NOT implementation, we need to use a NAND. And if you try well, as I said, answer for this question will be 5. So if you see here, just for our convenient, let us group AC because A and C are not having complement. So that let us rewrite it is AC and with B complement. Let us start the work like this. Consider AC is available. We'll see how to get AC later. Consider B bar is available. Hence, this gate output will be AC and with B bar complement. So, while using one more gate as an inverter, we are looking here. This is AB complement C. It is the one what we need as F. It is a need. It is the one what we want to implement, or it is a question what we are having. Now come back. How to get B bar is known for us. To get the B bar, we need to use an AND gate as a NOT gate. How to use an AND as a NOT gate, just now we learned. And to get AND operation between A and C, we need two NAND gates. So if you count the number of gates we are having as 5. So that answer to this question is 5. The answer to this question is 5. So whenever we are having a question of this, no need to develop the full circuit. After developing full circuit, we should not speak the answer. With our knowledge, just developing the partial circuit, we are having possibility to speak the answer on this question. While developing this partial circuit, this part of the circuit, we must be in a position to speak the answer on this question. After developing this partial circuit, we know to read B complement, we need 1 9. To get AC, we need 2 90 gates. So while counting these gates, we'll be speaking answer to this question is 5. Such a practice is expected. So every second is important in the exam hall. So wherever possible, you have to cut down the time. If you manage the time well in the exam hall, definitely your score will be good. You'll be getting enough time, reasonable time you'll be getting to recheck your answers, or maybe you are having special emphasis on few of the questions which are little complex or doubtful questions. On those things you can spend the time. So every second is important in the exam hall. Anyway, the answer to this question is 5. So let us try a few more questions. Note down. The minimum number of the minimum number of 2 input NAND gates required. Minimum number of 2 input NAND gates required to realize the function f, where the function f is w complement or z complement and with x or y, where the function f is w complement or z bar and with x or y. The minimum number of 2 input NAND gates required to realize this function is a question. Try with proper emphasis, with the proper attention. If you try, the answer to this question must be 4. Answer to this question must be 4. It was the question in the 1998 GATE EC paper for 2 marks. So 1998 means 22 years back. 22 years back means few of you might be not born. If you are appearing GATE exam 2021, then few of you might be not born. So it was a question in the 1998 GATE paper. The answer, if you try, as I said, the answer is 4. Let's look how it is. This f, I can write the first sum term as WZ whole bar. I'm writing the first sum term as WZ bar, of course, using De Morgan's property. And other sum term, let me write as it is at this point. Just for our convenience, let us name this WZ whole complement as something M. Hence, I can read with the expansion, this will be MX with MY. So we are having initially the given function, it was in the POS form. With this modification, mathematical manipulation, this POS form, we are changing it to SOP form. Once we are changing it to SOP form, almost answer is completed. This SOP expression we are having possibility to implement with a two-level 9 circuit. This SOP expression possible to implement with a two-level 9 circuit. I will speak what the means of this two-level 9. So it is standard circuit. If you look here now, this is a gate 1, this is a gate 2. The gate 1 input, if you look here, one is X, other input is M. Gate 2, one input is Y, one input is Y, and other input is M. So here it is MX complement, here it is MY complement. Later we are having the usage of one more gate. Let me name it as a gate 3. Gate 3, one input is gate 1 output, other input to the gate 3 is gate 2 output. So we are having here a question as similar to the previous question. The implementation we want using only minimum number of 2 input NAND gates. The questions what we are looking is just using only minimum number of 2 input NAND gates. And why we are taking this as the questions after discussing of these universal gates is to understand just using only NAND gates, or we are going to look little later, just by using only NOR gates we are having possibility to implement any function or in general any digital system. So for that purpose, basically we are discussing these questions. Of course, it happened to be the questions in the gate paper. So here in the previous question, we are looking this question, implementation just by using only NAND gates, that too only 2 input NAND gates is a constraint. Here also we are looking at a question, this implementation of the function we want with only NAND gates, that too only 2 input NAND gates. Okay. Anyway, if you back to this question. Now, if you look to the input to the output, total 2 levels. So that I must name this is a 2-level circuit. To read the output, the signals are passing as is from a 2-level circuit. This is a level 1. At level 1, we are having 2 NAND gates, they are in parallel. And this is level 2. At level 2, we are having 1 NAND gate. So overall circuit is a 2-level circuit. At level 1, at level 2, at both the places we are having NAND gates. Hence, I must speak this as 2-level NAND circuit. I must speak as a 2-level NAND circuit. Coming to the question. So one input is are having MX complement. Other input is MY complement to this third gate. So that MX complement and with MY complement overall complement. And it is effectively using De Morgan's property MX or with MY. It is the one what we are expecting what we want from the circuit, that is F. That is the F. Okay. And of course, we are having the usage of here the intermediate term M. M is WZ bar. So this WZ bar to get, we need one more 9. This 9 gate inputs are W and Z. So we are having here M, we know it is WZ bar. Hence, we are looking the total number of NAND gates required to realize the function F, where F is W bar or Z bar, and with X or with Y. So don't read as W bar plus Z bar into X plus Y like that. Don't read. You are engineering student. So most of you might be completed. So when we are talking such things, be clear. Technically, you have to be very clear to speak. Wrongly don't speak as plus plus. They are not arithmetic additions. They are logical operators. They are OR operators. So we need to talk as W bar or Z bar and with X or with Y. Okay. See, few of you maybe tomorrow maybe good teachers. And when you are teaching like us, if you speak as W bar plus Z bar and with W bar plus X bar, sorry, W bar plus Z bar and with X plus Y, like that if you speak, the students also will learn in the same way, and finally it will continue like this. Is chain process, a cascading effect will be there. So better avoid, use proper wording. Anyway, if we are looking to the question, the answer to the question is 4. While looking to this, let us continue little more on this question. For this question, answer is okay, but related to this, I'm talking. This 2 level 99, what we are looking here, this is basically implementing this function F. The implementation of this function F possible based on this, you can see for MX purpose, we will be using one int. For MY purpose, one int. Among these, for OR operation, we need one OR gate. So if at all we are developing circuit instead of using NAND gates, using AND gates and OR gate, the circuit will be like this. I will write here. So we are looking here first generating of these products. So one product need to be MX, other product need to be MY. So this is X, this is Y, this is M. Later, among these two terms, we want OR operation to read F, hence OR gate. So this circuit also we suppose name as a 2-level circuit, because at level 1 we are having 2 gates in parallel, they are AND gates. At level 2 we are having a OR gate. The literals, as I said earlier, just referring to only this part, don't get confused. As an engineering student, for same circuit you have to look many things. That is the best way of learning. Looking to everything as separate, it is not integrating. So subject anyway, as engineer you need to have the vast knowledge because of many subjects. So our learning also in the same direction, in the same approach. Not small level we have to look. Little higher level we have to learn. Then only you will be covering syllabus well, even examination point of view. So this is a 2-level 99. This is supposed to be named as a 2-level and OR. It must be named as a 2-level and OR. So from this you are having a conclusion. A 2-level and OR possible to replace with a 2-level 99 circuit. A 2-level and OR possible to replace with a 2-level 99 circuit. Are possible to speak a 2-level 99 is equivalent to a 2-level and OR circuit. A 2-level 99 is equivalent to a 2-level and OR circuit. So this is the conclusion what we are having while working on this question. As similar to this, we are going to discuss one more question. There, we'll try to understand a two-level NOR is equivalent to a two-level OR AND. Or two-level OR AND can be replaced with a two-level NOR. That we'll try to understand while working one other question. So at this, as it is at this point, it is a conclusion. So let's move to the next question. Next question is, realize the given Boolean function y. Realize the given Boolean function y using minimum number of two input NOR gates. Realize the given Boolean function y, where y is CRAB, using the minimum number of two input NOR gates. Even it was the question in the 97 GATE paper. This sort of things may be questions multiple choice or maybe fill in the blank as a numerical question. I mean, the present GATE pattern is concerned as a numerical question. So here you can see the given function, you can speak, it is in the SOP form. Using properties, you can look this alternatively as CA and with CRA and with CRB. So by using basically De Morgan's property, the given equation we can possible to read as CR with A and with CRB. So this expression, of course, POS form. So the given expression is in the SOP form. We are converting that with the properties with the POS form. It was the similar work what we had in the earlier question. It was a POS, the given expression we converted to SOP form. Now this POS expression possible to implement with a two-level NOR. And before coming to that, the answer to this question, if you look, definitely you have to speak the answer to this question as 3. When we are looking, the expression was SOP, we were using two-level 9-9 circuit. When the expression is in the POS, we are having possibility to use two-level NOR circuit. So if you look here, is a gate 1, is a gate 2. So gate 1, inputs, if you look here, C and A. Gate 2 inputs are C and B. Hence we are looking here C or A complement. This is C or B complement. Later, one more NOR we are using. Let us name the NOR gate 3. NOR gate the one input is from the gate 1 output, other input is from the gate 2 output. So gate 3 output, we are looking C or A complement or with C or B complement, whole complement. So if you work out well, the De Morgan's property, this will be C or A and with C or B. It is the one what we need as Y. It is the one what you need as a Y. So to realize the given function Y, total number of NOR gates we need only 3. We need only 3. Hence the answer is 3. And of course, as similar to the previous discussion, we must speak this as 2-level NOR circuit. This must be a 2-level NOR circuit. At level 1, we are having 2 NOR gates which are parallel at level 2 this. Okay. Here we are having some terms, so 2 gates. Suppose POS expression we are having the 3 sum terms, then 1 more NOR gate will be there. If we are having POS with 4, so 2 more. So anyway, at level 1 we are having set of NOR gates, at level 2 single gate. Whether the PO is consisting of 2 terms, 2 sum terms or 3 term sums, it is not the matter. The circuit is effectively resulting as 2-level NOR circuit. The same thing even here also. Here SOP is having 2 product terms, so 2 gates at level 1. If the SOP consisting of say 3 product terms, so 1 more gate will be added in parallel with the 1, 2. If the SOP is having 4 product terms, so 2 more gates will be added in parallel with the 1 and 2. Okay, the SOP may be of 2 terms, 3 terms or 4 terms. Effectively the shape of the circuit, if at all you are looking, at level 1 we are having parallel gates, at level 2 single gate. So on the whole the circuit is a 2-level circuit. We are using all the gates as 9 gates, it becomes a 2-level 9-9 circuit. It is a situation for SOP. If at all we are having the usage of the NOR gates, all NOR gates, of course it is on the POS, then it is 2-level NOR circuit. And alternatively you can look here, because of POS, for implementing of CA we need 1 OR gate, for implementing of this CRB we need 1 OR gate, for implementing of CRA, OR operation between C and A, for implementation of the OR operation between C and B, 1 OR gate. Later we need for AND among these sum terms. So you can look easily based on this. At level 1 we must use OR gates. So if we name it as a gate 1, if we name it as a gate 2, here we need C or A term as a result. Here we need CRB term as a result. Hence, this is A, this is B, it will be C, this will be C. At level 2, we need a AND gate, because AND operation we need among these 2 sum terms. Then only we are having it is Y as C or A AND with C or B. So definitely we are looking, it is also a 2-level circuit, it is also a 2-level circuit. And at level 1 we are having the usage of the OR gates, at level 2 AND gate. Based on this we supposed to speak this is 2-level OR AND circuit. 2-level OR AND circuit. At level 1 OR gates, at level 2 AND gate. So 2-level OR AND circuit. So we are having a conclusion. A 2-level NOR circuit is equivalent to a 2-level OR AND. Or a 2-level OR AND circuit can be replaced with only universal logic gates. Just by using only NOR gates we can replace. Hence conclusion is a 2-level NOR circuit is equivalent to a 2-level OR AND Similarly, a 2-level 9-9 circuit is equivalent to a 2-level AND OR circuit. So these are the conclusions we are having. As similar to these 2-level circuits, we must speak even for any other sort of 2-level circuits. We must able to speak about any other sort of 2-level circuits as similar to this. If somebody is asking a question, what is if somebody is asking a question, we are having a 2-level 9-NOR circuit. If you are having a 2-level 9-NOR circuit, its equivalent is what? Suppose somebody is asking as a question. If that is a question, it is a question to you in the exam paper or somewhere else in the interview. So the work what you need, at level 1 we are supposed to use NAND gate. At level 2 single NOR gate. At level 1 NAND gates, at level 2 only NOR gate. A simple circuit you need to make. Suppose if you do that, 2 gates let us use at level 1. So one gate inputs AB, other gate inputs CD. So this is AB complement, this is CD complement. At level 2 we must use a NOR gate. So we are having here at level 1 NAND gates, at level 2 NOR gate. On the whole, the circuit must be named as 2-level NAND NOR. We must speak it is a 2-level 9-NOR circuit. And we are looking here the output. We are having here it is AB complement or with CD complement whole complement. So this will be AB and with CD. It is AB and with CD by using De Morgan's property. So what we are looking, this 2-level 9-NOR circuit is resulting to be a AND operation. It is resulting to be a AND operation. Like this, we need to answer if at all any unknown thing. These are the standard circuits, 2-level 9-9, 2-level NOR. If any unstandard circuit, something is asked in the question paper or somewhere else, we are facing this as a question. It's a way you have to think. It's a way you have to look. So at level 1, minimum 2 gates you have to take. At level 2, single gate you have to take based on the question. Later, while looking to the output, it is possible for us to speak what is the answer on that question. So like this, we need to answer.